Hello, my name is Jonathan McGowan. This is going to be project 3 for EAS 3810C. In this project, we go over two different types of analysis of a flat plate. We do a analysis at a motor frequency of 20 hertz for the wind tunnel and a motor frequency of 50 hertz. And in this geometry that you see here that I'm going to go over, the reason that the test section or the actual whole wind tunnel isn't here is because when you're doing the meshing for the geometry, you want to make sure that you have a very refined mesh at where the boundary layer is going to occur. So in order to do that, I needed to kind of decrease the overall geometry into just the test section, so then I can refine it a little bit more. So all the results should be the same. It's just I've condensed it more, so it's a little bit easier to get our results. And after doing this, the results I had were more accurate to the calculated results. So first and foremost, our plate here that we're going to be using is 0.06 inches in height and 6 inches in length in a test section that is 12 inches long and 6 inches tall. In order to create this overall geometry, my method was to first draw the plate as a tiny rectangle, then use the dimensions tab, which should be right here. You click general, and then you can pretty much click and drag off any of these little lines and just adjust the dimensions. So here H8 is 6 inches, H14 is 3 inches, so we have 3 inches here, and then we know that from the back of the plate to the end is another 3 inches, or H17 would just combine those two to be 9 inches. And basically, yeah, you can just work with your geometry that way until you get this general shape. Make sure initially that you know your coordinate system, because when you move to doing lines or specific lines to show the boundary layer, you need to know the coordinates in meters. So make sure to take notes on that. Let's see here. Also, I'm seeing it's 0.006, not 0.06. Mess that up a little bit. The reason we have such a thin thickness at the front is because we want to reduce the pressure drag just so we can focus on the boundary layer formation and the boundary layer thickness, which is a lot easier to do when you have a thin flat plate. So once you have this geometry set up, I'm actually going to go back to the modeling. Yeah, once you have the overall shape set up, you can go to your surface from sketches. So you just go to concept, surfaces from sketches, and then you basically just go to this box select tool right here, and you can highlight it, and then it should leave your flat plate kind of open while the rest of it turns like a darker color. And once that is complete, you then can move on to the next step, which will be, let me actually open that up really quick. The next step is meshing. So we're going to go to our mesh. Here we have our shape. I'm going to click the mesh again. So as you can see, I've already done the meshing ahead of time. I'm going to show you how I got to this mesh. This mesh, like I said before, is very refined as opposed to the test, the whole wind tunnel as a one geometry. You don't get as much detailed in the mesh, which again isn't that great for the boundary layer. So when I zoom in on this, as you can see, we have a lot of tiny little meshes and cells here, which is going to be a good indicator that our boundary layer is going to be very well defined and have accurate values. So first, to get this, you want to right click, you want to go to insert, you want to go to method. Once you have method down here, you can click on method and you can just click generate. It'll generate a general mesh with a couple cells. But in order to refine that and get it a little bit more precise, you can go down to your element size and just make it 0.001 meters for this specific geometry. And that should give you these nice little tiny cells. In order to refine it a little bit more, you can right click on mesh, go to insert and refinement. Once you click refinement, you can go down to here. Refinement level 1, I think, should be necessary. If you wanted to go a little bit more in depth, you could do refinement level 2 or 3, but for my computer processing, it would just be better at 1. You click generate, and the mesh you see here is the result of the automatic method and the refinement. Next, you need to go to the name selections. So in order to do name selections, you can just click this little icon here. You can select edges. So like you can select this edge, for example. You can select this edge, and you can basically right click and click create name selection, and that'll basically just label your wall. So here we have the inlet, the outlet, we have symmetry, top and bottom. We have our top of the plate, our bottom of the plate, which looks the same from this distance in, but I can zoom in and show you. Our bottom of the plate is turned red. And then our front is the front part of the plate, which you can't see because it's zoomed out, and the back part of the plate is here. And once you have all this complete, you're pretty much ready to go to the analysis portion. So in order to do that, we're going to go to Fluent, which I already have set up. In order to get a proper setup, I'm going to be showing you how to do this. You go to, for the models, you want to choose laminar flow. Click laminar. Then we're going to go to the materials, fluid, air. Your default is going to be 1.225 kilograms per meter cubed, and your default viscosity is going to be a little bit smaller than this. In order to get a more defined boundary layer, though, I decided to kind of make these things a little bit more consistent, and the Reynolds number was actually a little bit easier to solve for as well. So I changed the density to 1 kilogram per meter cubed and viscosity to 1 times 10 to the negative 4. Close this out. Next, we have to go to boundary conditions. We have to make sure that our inlet is a velocity inlet. Click edit. Our velocity is going to be absolute. I believe that's what I kept it as. And then our test section velocity corresponding to a motor frequency of 20 hertz is 4.6062 meters per second. Close that. Make sure our back, bottom, front, and top are all walls, and that our outlet is a pressure outlet as well. Going to our reference values, we want to make sure we calculate from our inlet, like so. We then go to initialization, initialize, hybrid initialization is preferred, and then you want to go to run calculation, making sure that your calculation has approximately 100 iterations, 60 in this case because it converts relatively quickly. Following this, we're going to make a surface. We're going to make two surfaces. We're going to make lines. We're going to make the endpoint line, which I'll open up really quick. These coordinates are in meters, so in order to remember that coordinate system I said in the geometry, this is where it's going to come into play. Our origin for this coordinate system is at the bottom left center, or bottom left part of the plate, which is at origin 0, 0. So we need to get a line at the midpoint of the top plate so we can identify the boundary layer and its thickness. And these are the coordinates here. 0.15. Oh, this is the endpoint actually. So this will be at 6 inches. We have x equals 0.1524. And we have y beginning at 0.02. And then our other point is at, again, x equals 0.1524. And then our y is at the very, very top of the plate, which is approximately 0.006 inches, which is approximately equal to this number here. And you do the same thing with the midpoint. Going to plots, we can go to XY plots, which is down here. You can go to your midpoint graph, which I will upload really quickly. Save and plot. Move this down so we can see our graph here. That right there, perfect. And as you can see against our curve length of the top plate, you see that this boundary layer begins to form. You can adjust these parameters a little bit more just so you have that actual boundary layer looking shape rather than a downward facing parabola or downward facing curve. And this, I believe, is the wall shear stress. So I'm going to save and plot that. This is our wall shear stress. As you can see, towards the front of the plate, we're going to have a greater shear stress just because our boundary layer isn't going to be as defined, so our viscous effects are going to be more dominant. We'll minimize that. In order to get the next portion of this project, you have to go to, actually first let me show you how to get the forces, because that's actually necessary. You go to the reports, forces, and you just print your forces here. You go back over here, and we'll put this up into here. And these are all your forces. So like your total force for this, your total drag coefficient would be 0.010141931. And as you can see here, most of this drag coefficient comes due to the viscous force, which is as expected because we have a streamlined body. So once this is complete, you then have the ability to go to your results section. And in your results section, we have to do a couple things. We have to one way to check your lines to make sure they're proper when doing, before, you know, I had to do the midpoint and coordinates. You can actually come in here and it shows you where the line is located. So for here, I have the midpoint and the endpoint. And this was just me checking to make sure those coordinates were correct in the other, in the Fluent. So in order to get this velocity contour, which is required for this tunnel, you need to first go to contours. You just click this. You click velocity, and then it'll bring you to this thing here. You want to choose your velocity, obviously. Location needs to be at symmetry 2. Let's put that back to symmetry 2. Right there. Okay. And then we're going to scroll down to the bottom here, making sure our contours that are approximately, as long as they're greater than 100, you'll be okay. And then you'll get this shape here. And when we zoom in on this boundary layer, as you can see in the front of the plate, you're expected not to have a significant thickness of the boundary layer. But as it propagates outwards towards the end, you see we get a little bit of a wake region, a little bit of flow separation, and we get a larger boundary layer thickness. So that is that. Then you need to also do the vector, velocity vector. So we're going to minimize that and go to here. This is our vector trail, which will show you kind of how thick the boundary layer is, but with vectors. So it's a little bit easier to see where the airflow is going. To do this, you can just click the vector tab here, and it will open a tiny tab at the bottom. Again, you choose symmetry 2. Go down. Factor of 1 should be okay, just because there's enough vectors there for you to get the general idea. And you can just click apply, and this will be your result. And when you zoom out a little bit, you can kind of see the general trend of how the airflow moves. So after this is done, I just went and did my calculations. So I'm going to minimize all this really quickly and show you project 3. Give it a second here. Once it loads, hopefully. All right, so this is all the data that has been extrapolated from Fluent. In order to do that, you can just write all of your graphs in that results section to a file and then kind of upload it into Word. So here we have our 20 hertz, we have our shear stress against our top plate. We have our midpoint line, which is our velocity profile at the midpoint and at the end point. And then here we have our skin friction coefficient for 20 hertz. Then over here you have your 50 hertz all the way to column AC over here. And in order to do your actual calculations, all the calculations and sample calculations will be provided in the report. But you can just kind of use these values and compare them and see how your simulated results compare to your theoretical results. And with that, I'm going to stop the recording. Thank you so much for watching, and I'll see you in the next video.